The Chatelier's principle. So follow along with this video to complete your notes, and keep in mind that if you need to pause the video, you can in order to catch up. Once you are finished, you will write a summary of your notes. So our first question is, what is a stress on a system that is at equilibrium? So a stress is something that causes a change in the equilibrium mixture. So when we say equilibrium mixture, we're referring to the relative amount of products and reactants that are present. So this can be due to a change in the concentration of a reactant or a product, something is added or removed, temperature, raising or lowering temperature, and pressure, which is only going to have an impact on gaseous reactions. So the equilibrium position may be pushed to favor either reactants or products by applying a stress to a chemical system. So we can use a stress to change that mixture. So let's start with how changes in concentration affect equilibrium. So I have a chemical reaction here. This is the formation of carbon dioxide and water from carbonic acid. And we want to know what happens if we change the concentration of something. So you should remember, if you add something, the equilibrium is going to shift away from it to use it up or to get rid of it. If you remove something, the equilibrium is shifting towards it to replace it, to make up for what you took away. So if we were to add carbon dioxide, notice that carbon dioxide is a product here. So if we add CO2, the equilibrium is going to push away towards the reactants. What if we remove CO2? So if we take CO2 away, the equilibrium is going to shift to replace that carbon dioxide that was removed. So if you add, you shift away. If you remove, you shift to replace. What about changes in temperature? How do those affect the equilibrium? So I have a chemical reaction here. This is the Haber process that produces ammonia, very important reaction for making enough fertilizer to grow food for our population. And this reaction is exothermic. Heat is a product. So just like before, if you add heat, we're going to shift away. And if we remove heat, we shift to replace. So that same concept as we looked at with concentration still applies here. So if I were to take the heat and increase it, I would be increasing the amount of heat, which will push the equilibrium to the side of reactants. What if I remove heat? We're going to shift to produce more heat to replace what we took away. Now, this can be represented in a couple different ways here. All three of these are giving you the same equation and the same information. Here we just have heat as a general term. Here we have an actual number for the amount of heat, and here we have it written separate from the reaction. The way that these are all three written, you should be able to tell are all exothermic, and heat is a product. So let's look at pressure. So pressure is going to only have a big impact on gaseous reactions. And they have to have an uneven number of moles on each side of that double arrow. So if we increase the pressure, we're going to shift to the side that has fewer moles of gas because that will help to reduce the pressure. If we decrease the pressure, the system's going to try to respond in a way that makes the pressure go up. So it's going to shift to the side that has more moles of gas in order to increase the pressure. So looking at this equation here, I've got 4 moles on my reactant side. I've got 1 mole of nitrogen and 3 moles of hydrogen. So that's 4 moles total. And on the product side, I only have 2 moles here. So if we were to increase the pressure, the system's going to shift to the side that has less gas so that the pressure will go back down. If we decrease the pressure, the system tries to respond in a way that makes the pressure go back up. So it's going to shift to the side that has more moles of gas. If they have the same moles on both sides, then changing the pressure is not going to impact the equilibrium there. So the next question is, how do catalysts impact equilibrium? So catalysts do not change the equilibrium position. They just help us get to equilibrium faster. So catalysts decrease the time that it takes to establish equilibrium, and they do this by lowering activation energy. So we'll get to equilibrium faster, but it doesn't actually change our equilibrium conditions. Our equilibrium conditions, that is the ratio of reactants and products present at equilibrium, is determined by that equilibrium constant K. So a catalyst is going to reduce the activation energy, which speeds up the reaction. So here we see an enthalpy diagram that's showing us a reaction with and without a catalyst. And we see that hill that the reactants must overcome, that energy hill, is a little bit smaller. That means it has a lower activation energy. So the size of that hill is our activation energy. So how do catalysts do that? Catalysts will actually grab onto the reactants and hold them in the correct orientation so that they're able to react with less energy. So we looked at this whenever we were talking about reactions and how to affect the rate of a reaction. So go ahead and process your notes by writing a summary. Your summary should include the following: ways to shift a reaction to favor reactants or products, and how to predict the direction of the shift when each type of stress is applied.